First of all, I would like to thank Harun for the invitation to give this talk. And I think the title is a bit too broad because all I'm going to do is to show how to formally derive the compressible Euler systems. So the structure of the talk is the following. I'll start with a brief introduction of the kinetic theory, which will lead to the talk about the Boltzmann equation. And then in the second section, I will just give a list of the properties of the Boltzmann's collision integral that I will use in what I will develop in the other part of the talk. In section 3, I'll show how to write the Boltzmann equation in scaled or dimensionless form. And in the last section of the talk, I'll show how to formally derive the compressible Euler equations. All right. The kinetic theory is a branch of non-equilibrium statistical physics. It deals with the modeling of a gas or plasma or any system that is composed of a very large number of particles. In this talk, the interest is on the kinetic theory of gases. One of the main objectives of the kinetic theory of gases is the description of macroscopic properties of gases, such as temperature, pressure, diffusion, viscosity, thermal conductivity, and so on, from microscopic quantities that are associated with the molecules that composes the gas, such as velocity, kinetic energy, internal degrees of freedom, and interactions between the molecules. In the kinetic theory of gases, the Boltzmann equation is the model that governs the evolution of the distribution of molecules in a perfect or ideal gas. The unknown of the Boltzmann equation is a non-negative function f that depends on t, x, and v, called the velocity distribution function. Here, t is the time variable, x is the space variable, and v is the velocity variable. The velocity distribution function represents the density of molecules which at time t greater than or equal to 0 are located at position x in arrow 3 and have velocity v in arrow 3. This velocity distribution function changes as a result of two processes, namely free streaming of the molecules or free transport of the molecules and collisions between the molecules. To describe how the velocity distribution function changes as a result of free transport of the molecules, we use the fact that, according to Newton's first law of motion, in the absence of external forces, each molecule travels in straight line with constant velocity, and the density is constant along the characteristic lines, the x over the t equals v, and the v over the t equals 0. Thus, one can compute the value of the velocity distribution function at time t in terms of its value at time 0 to obtain the following expression. In other words, the velocity distribution function is a weak solution of the free transport equation, which is given as follows. Now, of course, when there is a macroscopic external force acting on the molecules, the free transport equation has to be adjusted accordingly, since the trajectories of the molecules are no longer straight lines. Therefore, in this case, the relevant equation will read as follows, where f of x is the macroscopic external force acting on the molecules. This equation is often referred to as the linear Vlasov equation. Now, to describe how the velocity distribution function changes as a result of collisions between the molecules, Boltzmann used the following assumptions. 1, only binary collisions between the molecules are considered. This assumption simply means that collisions involving more than 2 molecules are not taken into account. 2, the collisions between the molecules are localized both in space x and in time t. This assumption simply means that collisions between the molecules are assumed to be brief events that occur at a given position x and at a given time t. 3, the velocities of the two molecules that are about to collide are uncorrelated. This assumption is often referred to as the Boltzmann's chaos assumption. 4, collisions between the molecules are elastic. This assumption means that collisions between the molecules, linear momentum and kinetic energy are both conserved. The conservation laws of linear momentum and kinetic energy are respectively given as follows, where V and V star are the pre-collision velocities, that is the velocities of the molecules before collision, while V prime and V star prime are the post-collision velocities, that is the velocities of the molecules after collision. The post-collision velocities are defined in terms of the pre-collision velocities, and the formulas for the post-collision velocities are given as follows, where omega is an arbitrary unit vector. The fifth assumption states that collisions between the molecules are micro-reversible. This assumption simply means that the probability that the pre-collision velocities are changed into post-collision velocities is the same as the probability that the post-collision velocities are changed into pre-collision velocities in a collision event. Using these 5 assumptions, Boltzmann in 1872 was able to derive a quadratic collision operator, which accurately modeled the effect of molecular interactions on the velocity distribution function, and it reads as follows. In the definition of the collision integral, I have used the following abbreviations. In particular, I have suppressed the dependence of the velocity distribution function on the time and space variables. The function B that depends on the absolute value of the relative velocity and omega is a non-negative function called the collision kernel. And again, omega is an arbitrary unit vector. From the structure of the collision integral, one can easily trace back the modeling assumptions used by Boltzmann for its derivation. In particular, the quadratic nature of the collision integral is due to the fact that only binary elastic collisions are considered. 2, the fact that the parameters x and t only appear as parameters reflects the assumption that collisions between the molecules are assumed to be localized both in space x and in time t. 3, the appearance of the products f of v prime times f of v star prime and f of v times f of v star is the consequence of the Boltzmann's chaos assumption. 4, the assumption of elastic collisions between the molecules results in the formulas for the post-collision velocities. And 5, the micro-reversibility assumption implies the particular structure of the Boltzmann's collision kernel. The formulas for the post-collision velocities represent all the solutions of a system of equations, which is comprised of the conservation laws of linear momentum and kinetic energy, respectively. To see this, recall the conservation law of linear momentum and kinetic energy, which are respectively given as follows. V plus V star is equal to V prime plus V star prime. And absolute value of V squared plus the absolute value of V star squared is equal to the absolute value of V prime squared plus the absolute value of V star prime squared. This implies that the absolute value of V prime squared plus the absolute value of V star prime squared minus the absolute value of V squared minus the absolute value of V star squared is equal to 0. Let's call this equation 1. These conservation laws impose 4 constraints on the 6 variables V prime and V star prime. Therefore, there are 2 degrees of freedom Now, if we write V prime to be equal to V plus A times omega and V star prime to be equal to V star minus A times omega, let's call this equation 2, where A is the function of V star, and omega is an arbitrary function, is an arbitrary scalar function, is a scalar function to be determined and absolute value of omega is equal to 1. Now observe that by summing these 2 equations given in equation 2, one automatically obtains the conservation of momentum. So now we need to force the conservation of kinetic energy. To do this, observe that absolute value of V prime squared is equal to absolute value of V plus 2 times A times V dot omega plus A squared. We call this equation 3, and absolute value of V star prime squared is equal to absolute value of V star minus 2A times V star dot omega plus A squared. We call this equation 4. Now, adding equations 3 and 4 gives the following. Absolute value of V prime squared plus the absolute value of V star prime squared is equal to the absolute value of V plus the absolute value of V star plus 2A times the difference of V dot omega minus V star dot omega plus 2A squared. We call this equation 5. Equation 5 can be rewritten as follows. Absolute value of V prime squared plus the absolute value of V star prime squared minus the absolute value of V squared. Oh, sorry, here I'm missing the squares here. Plus the absolute value of V star squared is equal to 2A times the difference V dot omega minus V star dot omega plus 2A squared. We call this equation 6. Using equation 1, we can rewrite equation 6 as given below. 2a times the difference v dot omega minus v star dot omega plus 2a squared is equal to 0. Dividing both sides of this equation, okay, let's call this 7. Dividing both sides of 7 by 2 and factorizing, we arrive at a times a plus v minus v star dot omega is equal to 0. Therefore, either a is equal to 0 or a is equal to minus v star dot omega. Hence, so long as a is different from 0, we have from equation 2 that v prime is equal to v minus v star dot omega times omega, and v star prime is equal to v star plus v minus v star dot omega times omega, which are the expressions or the formulas for the post-collision velocities. Now, putting together the free transport equation and the collision operator, we obtain the Boltzmann equation. The Boltzmann equation is a nonlinear integral differential equation that describes how the velocity distribution function changes as a result of free transport of the molecules and collisions between the molecules. Now, let us study some of the properties of the Boltzmann's collision operator that will be useful for what will be developed in the later part of this talk. The first of these properties is given in the following proposition. Let psi be an arbitrary function of the velocity variable such that the following integral makes sense. Then the weak form of the collision integral is given by the following expression. This result is essential to understanding the Boltzmann equation, especially the relation of the Boltzmann equation to hydrodynamics. And for this reason, I'll give a complete step-by-step proof of this result. Proof: multiplying the collision integral given below by an arbitrary function of the velocity variable and integrating the resulting equation over all possible values of the velocity variable, one obtains the following equation. Now, switching v and v star in the integrals on the right-hand side of this equation, that is in this integral, we obtain equation 2. To obtain equation 2, the fact that the collision kernel is invariant by switching v and v star have been used, together with the fact that f of v prime, in particular v prime, transforms into v star prime, while v star prime transforms into v prime by switching v and v star. To see this, recall the formulas for the post-collision velocities V prime is equal to V minus V minus V star dot omega times omega. Call this equation 1. V star prime is equal to V star plus V minus V star dot omega times omega. Call this equation 2. Observe that switching V and V star in equation 1 above, gives V prime is equal to V star minus V star minus V dot omega times omega. This is equal to V star minus V minus V star dot omega times omega. This is also equal to V star plus V minus V star dot omega times omega, which is equal to V star prime from equation 2 above. Similarly, switching V and V star in equation 2 above gives V star prime is equal to V plus V star minus V dot omega times omega. This is equal to V plus minus V minus V star dot omega times omega. And this is equal to V minus V star dot omega times omega, which is equal to V prime from equation 1 above. So we have just shown that V prime transforms into V star prime, while V star prime transforms into V prime by switching V and V star in the integral on the right-hand side of equation 1. That is this equation. Next, we use the following change of variables in the integral on the right-hand side of equation 1 given in the previous slides. In particular, using the transformation of the pair V star to V prime star in the integral on the right-hand side of equation 1, we obtain the following equation, where the fact that the Jacobian of the transformation of the pair V star to the pair V prime V star prime has absolute value of 1 has been used. Now observe that the collision kernel is also invariant under this transformation. Now to see that the collision kernel is invariant under this transformation, again, observe that absolute value of V minus V star squared is equal to absolute value of V squared plus absolute value of V star squared minus 2V dot V star. This is equal to absolute value of V squared plus absolute value of V star squared plus the absolute value of V squared plus the absolute value of V star squared minus the absolute value of V squared minus the absolute value of V star squared minus 2V dot V star. This can be rewritten as 2 times the absolute value of V squared plus 2 times the absolute value of V star squared minus absolute value of V squared plus the absolute value of V star squared plus 2 times V dot V star. This is also equal to 2 times the absolute value of V squared plus 2 times the absolute value of V star squared minus the absolute value of V plus V star squared. Now, applying the conservation of kinetic energy to the first 2 terms and the conservation of momentum to this term, we obtain that we can rewrite this equation as 2 times V absolute value of V prime squared plus 2 times the absolute value of V star prime squared minus the absolute value of V prime plus V star prime squared. And this is equal to absolute value of V prime minus V star prime squared. Now, taking square root of both sides, gives that the absolute value of V minus V star is equal to the absolute value of V prime minus V star prime. Therefore, B that depends on the absolute value of V minus V star and omega is equal to B that depends on the absolute value of V prime minus V star prime and omega. So the collision kernel is invariant under the switching, under the transformation of the pair V prime, V star to V prime, V star prime. Therefore, we can rewrite this equation. We can rewrite this equation as given below. Now, V and V star that depends on V prime, V star prime, and omega is given by the following formulas. To see how to obtain these formulas, again, we recall the definitions or the formulas for the post-collision velocities. V prime is equal to V minus V star dot omega times omega. We call this equation 1. V star prime is equal to V star plus V minus V star dot omega times omega. We call this equation 2. Subtracting equation 2 from equation 1 gives the following. V prime minus V star prime is equal to V minus V star minus 2 times V minus V star dot omega times omega. Therefore, V prime minus V star prime dot omega is equal to V minus V star dot omega minus 2 V minus V star dot omega times omega dot omega. This is equal to V minus V star dot omega minus 2 V minus V star dot omega. And this is equal to minus V minus V star dot omega, where the fact that omega dot omega is equal to 1 have been used. Now observe that from equations 1 and 2, V is equal to V prime plus V minus V star dot omega times omega. Call this equation, okay, let's call this equation 3 and call this equation 4, while V star is equal to V star prime minus V star dot omega times omega. We call this equation 5. Using equation 3 in equations 4 and 5 gives that V is equal to V prime minus V star dot omega times omega, prime. And this is equivalent to V that depends on V prime, V star prime, and omega. While V star is equal to V star prime plus V prime minus V star prime dot omega times omega, which is equivalent to V star that depends on V prime, V star prime, and omega. Therefore, substituting this expression, these formulas, into the integral on the right-hand side of the previous equation, we obtain the following equation. Next, we rename V prime and V star prime to V and V star in the integral on the right-hand side of the previous equation to obtain this equation. Now, recall the definition of the post-collision velocities, which is given below. Now, using this definition of the post-collision velocities, we can rewrite this integral as follows. Now, switching V and V star in the integrals on the right-hand side of this equation, we obtain the following equation, where again, the fact that the collision kernel is invariant by switching V and V star, and the fact that V prime transforms into V star prime, while V star prime transforms into V prime by switching V and V star have been used to obtain equation 4, in particular the integral on the right-hand side of equation 4. Now, summing equations 1, 2, 3, and 4, we obtain the following expression, which upon dividing both sides of this equation by 4, give the announced weak form of the Boltzmann's collision operator. The next property of the collision operator to be considered is given in this corollary. Let F be a solution of the Boltzmann equation that is integrable and rapidly decaying in V for each T and X. Then the following properties hold. 1, by multiplying the collision operator by the molecular mass and integrating the resulting expression over all possible values of the velocity variable, one obtains that it vanishes. 2, multiplying the Boltzmann's collision operator by components of momentum and integrating the resulting expression over all possible values of the velocity variable, one obtains that it vanishes. 3, by multiplying the collision operator by the kinetic energy and integrating the resulting expression over all possible values of the velocity variable, one obtains that it vanishes. Proof. Now recall the weak form of the collision integral, which is given below for convenience. Now, by setting psi to be equal to the molecular mass in the weak form of the collision integral, and using the fact that m plus m minus m is equal to 0 gives property 1. Also, setting psi to be equal to components of the momentum in the weak form of the collision integral and using the conservation of momentum gives property 2. Lastly, setting psi to be equal to the kinetic energy in the weak form of the collision integral and using the conservation of kinetic energy gives property 3. Now, let me introduce the notion of collision invariant. Sorry, before introducing the notion of collision invariance, the following remark is a consequence of corollary 2.2. In particular, the local conservation laws given below are immediate consequences of corollary 2.2. 1, local conservation of mass. The local conservation of mass is obtained by multiplying both sides of the Boltzmann equation by the molecular mass and integrating the resulting equation over all possible values of the velocity variable. 2, local conservation of momentum. This equation is obtained by multiplying both sides of the Boltzmann equation by components of the momentum and then integrating the resulting equation over all possible values of the velocity variable. And finally, the local conservation of energy, which is obtained by multiplying both sides of the Boltzmann equation by the kinetic energy, that is by 1/2v squared, and integrating the resulting equation over all possible values of the velocity variable. Now, let me introduce the notion of collision invariant. A collision invariant is a measurable function, psi, defined almost everywhere on arrow 3 that satisfies the following property. Now, from the result of corollary 2.2, we can infer that the molecular mass, momentum, and kinetic energy are examples of collision invariance. In particular, since the molecular mass is a constant, one can say that constants, momentum, and kinetic energy are examples of collision invariance. In particular, a function psi is called a collision invariant if and only if there exist constants A and C in R and B in arrow 3 such that psi of V is equal to A plus B dot V plus C times the absolute value of V squared. This proposition asserts that the above examples of collision invariants provide all the collision invariants up to linear combinations. The final property of the collision operator to be considered is the Boltzmann's H theorem. Let f that is greater than 0 be a locally integrable function that is rapidly decaying such that...
Benjamin, can I interrupt you for 1 second?
Yes.
I think there is a question in the chat. So
okay.
The question says, M has no role here. So can you just take it to be equal to 1?
That what has no role?
M, I mean, M is the mass, right? It doesn't depend on
yes,
the velocity.
M is the mass, yes. You can also multiply both sides because if you see the way the equations is, you can also take it to be 1 exactly.
Okay. I think does this...
Yeah, another reason why I left the M is because of the way I define the local Maxwellian. When I get there, you see.
Yeah, thank you.
Okay. Thank you.
Is there any other question? All right. So the Boltzmann's H theorem. Let f greater than 0 be a locally integrable function that is rapidly decaying and such that log f has at most polynomial growth as the absolute value of v tends to plus infinity. Then the following property holds. Moreover, the following 3 conditions are equivalent One, the collision operator vanishes for all V in R3. Two, multiplying the collision operator by log F and integrating the resulting expression over all possible values of the velocity variable, one obtains that it vanishes. And three, there exists an N that is greater than 0, a T that is greater than 0, and a U in R3, such that the velocity distribution function is of the following form, where N is the number density, Kb is the Boltzmann's constant, T is the temperature, U is the macroscopic velocity or the bulk velocity. Now, proof of the H theorem. Recall the weak form of the collision integral, which is given as follows. Now, setting psi to be equal to log F in the weak form of the collision integral, we obtain that it is a collision invariant. In particular, we obtain this equation. Now, since logarithm is an increasing function, we have that the following property holds. In particular, if A is greater than B, we have that this term is greater than 0, and also this term is greater than 0. So the product is positive. When A is less than B, we have that this term is negative, and this term is also negative. So the product is positive. While if A is equal to B, we obtain that this term is equal to 0, and this term is also equal to 0. So the product is equal to 0. Therefore, we obtain the following integral. In particular, the collision kernel is strictly positive, so the integrand in this integral is positive, is greater than or equal to 0, sorry. Therefore, because of the negative sign in front of the integral, we have that the entire integral is less than or equal to 0. This concludes the first part of the H theorem. For the second part of the H theorem, observe that if this term is equal to 0, we must have that F, the product F of V prime times F of V star prime must be equal to F of V times F of V star. And therefore, this implies that the collision operator vanishes, which accounts for the equivalence between conditions 1 and 2. To prove that condition 2 implies 3, we suppose that condition 2 holds. That is, we suppose that the following equation is true. Then if this equation is true, we have that log F is a collision invariant. And by the definition of collision invariant, we have that log F must be equal to A plus B dot V plus C times absolute value of V squared. If we take exponential of both sides of this equation, we obtain that F is of the following form. Now, if we set A to be equal to the following expression and set B to be equal to the product of the molecular mass times bulk velocity divided by the Boltzmann's constant times temperature, and set C to be equal to minus the molecular mass divided by 2 times the Boltzmann's constant times temperature, for N that is greater than 0, T that is greater than 0, and U that is in R3, we obtain the following form of the velocity distribution function, which is often called the local Maxwellian. Finally, to prove that condition 3 implies 1, we suppose that condition 1 holds. That is, we assume that the velocity distribution function is the local Maxwellian. Then observe that the following sum can be rewritten as follows. Now, applying the conservation law of kinetic energy to these first two terms, and the conservation law of linear momentum to this term, we obtain that this equation can be rewritten as follows. This implies that the product f of v prime times f of v star prime is equal to the product f of v times f of v star. Therefore, the difference of f of v prime times f of v star prime and f of v times f of v star is equal to 0, which implies that the collision operator is equal to 0, which concludes the proof of the H theorem. Now, the starting point for the derivation of hydrodynamic models or macroscopic models from the Boltzmann equation is the scaled or dimensionless form of the Boltzmann equation. Therefore, I will start this section by showing how to write the Boltzmann equation in scaled or dimensionless form. To do this, we need to first choose macroscopic scales that are associated with the independent variables of the Boltzmann equation. In particular, we need to choose macroscopic scales for the time, space, and velocity variables of the Boltzmann equation. To this end, let tau and L be the macroscopic scales associated with the independent variables, time and space, respectively. And let T0 be the macroscopic scale associated with the temperature T. These macroscopic scales define two velocity scales, the first of which is U0, which is equal to L divided by tau. U0 is the speed at which some macroscopic portion of the gas is transported over a distance L at time tau. And the second is the speed of sound in a monoatomic gas. It is denoted by C0, and it is defined as follows. Now, using these macroscopic scales, in particular, the macroscopic scales tau, L, and C0, one can define the dimensionless time, T hat, which is equal to T divided by tau. The dimensionless space, X hat, which is equal to X divided by L. The dimensionless velocity, V hat, which is equal to V divided by the speed of sound. The dimensionless velocity distribution function, F hat, which is equal to the following expression, where N is the number of molecules in a volume L cubed, and the dimensionless collision kernel, B hat, which is given by the following expression, where R is the molecular radius. Now, using the definition of the dimensionless velocity distribution function, we can rewrite the first term on the left-hand side of the Boltzmann equation as follows. Now, the factor multiplying F hat, that is this term, is a constant, so we can rewrite this equation, in particular, the right-hand side of this equation as follows. Now, using the definition of the dimensionless time, T hat, which is equal to T divided by tau, we obtain that taking the partial derivative of T hat with respect to tau, we get 1 all over tau. Taking the partial derivative of T hat with respect to time, T, we obtain that it is equal to 1 all over tau. Therefore, the previous equation can be written as follows. Rearranging the terms on the right-hand side of this equation, we can rewrite it as follows. Also, using the definition of the dimensionless velocity and the definition of the dimensionless velocity distribution function, we can rewrite the second term on the left-hand side of the Boltzmann equation as follows. Again, the factor multiplying F hat is a constant, so we can rewrite the right-hand side of this equation as follows. Now, using the definition of the dimensionless space, X hat, which is equal to X divided by L, we obtain that taking the partial derivative of X hat with respect to X, we obtain that it is equal to 1 all over L. Therefore, the previous equation can be rewritten as follows. Rearranging the terms on the right-hand side of this equation, we obtain that it can be given as it is given by the following expression. Also, using the definition of the dimensionless velocity, the definition of the dimensionless velocity distribution function, and the definition of the dimensionless collision kernel, we can rewrite the collision operator as follows. Taking the constants outside the integral sign, we obtain that we can rewrite the right-hand side of this equation as given below, or equivalently as follows. Now, putting together the first term on the left-hand side of the Boltzmann equation, the second term on the left-hand side of the Boltzmann equation, and the third term, in particular, the collision operator, we obtain that the Boltzmann equation can be rewritten as follows. Now, by multiplying both sides of this form of the Boltzmann equation by L to the power 4 times C0 squared divided by N, we obtain the dimensionless Boltzmann equation. Now, let me introduce the notion of the mean free path, which is the average distance traveled by a molecule between two successive collisions.
Can you please go back to the previous slide? I just want to take a look on the final equation.
Okay, this?
Yeah.
Okay. Now you are multiplying both sides of this equation by this guy. You see, this guy is exactly this, so they cancel out. You don't have it here, right?
Yes, yeah. Okay, yeah, all right.
Okay. So this is the dimensionless form of the Boltzmann equation.
Yeah,
now,
so again, the capital N is the number of...
is the number of molecules in a volume. So it's just a number, it doesn't have any dimension. So right, if you look critically to see that it's dimensionless, you see that this guy here has the dimension of velocity, which is meters per second.
Yes.
And this also has the dimension of velocity. So it's dimension of velocity divided by velocity.
Okay.
And here, the collision kernel has the dimension of area. So this is like area, which is meter squared.
Okay.
And this is length, which is meter squared.
All right. And tau, so, what is the dimension? For tau? Tau is a constant for you here? Or...
Tau is the macroscopic time scale. So you know speed or velocity is defined as distance all over time. L is the distance, that is the space macroscopic space variable, and tau is the macroscopic time scale.
All right, okay. All right.
So L divided by tau is like a velocity or a speed, which has the unit of meters per second.
Okay, got it. Okay, thank you very much, Mr.
All right. So now, the mean free path is the average distance traveled by a molecule between two successive collisions, and it is given by the following formula. The mathematical justification of this formula for the mean free path can be found in the following paper. Now, using the definition of the mean free path, we introduce a dimensionless variable called the Knudsen number, and it is the ratio of the mean free path to the macroscopic length scale. The Knudsen number is denoted by Kn, and it is defined as follows. Now, observe that the factor multiplying the collision operator in the dimensionless form of the Boltzmann equation given below can be rewritten as 1 all over the Knudsen number. Also, the factor multiplying the time derivative is called the kinetic Strouhal number, in analogy to the Strouhal number in the dynamics of vortices. It is represented by St and is given as follows. Now, by replacing this guy by St and this guy by 1 all over the Knudsen number, we obtain that we can rewrite the dimensionless form of the Boltzmann equation as follows. Now, if we removing the hats and replacing F by F epsilon so as to distinguish the scaled Boltzmann equation from the unscaled one, we obtain that the dimensionless form of the Boltzmann equation is given by this equation here. Now, if we set the Strouhal number to be equal to 1 and the Knudsen number to be equal to epsilon, we obtain the following scaling of the Boltzmann equation, which is called the hyperbolic scaling of the Boltzmann equation. This scaling of the Boltzmann equation is used in the derivation of the compressible Euler equations and the compressible Navier-Stokes equations. On the other hand, if we assume that the Strouhal number is equal to the Knudsen number and we set it equal to epsilon, we obtain the parabolic scaling of the Boltzmann equation. This scaling of the Boltzmann equation is used in the derivation of incompressible Navier-Stokes equation, incompressible Euler equations, and the acoustic equations. Now, let me show how to derive the compressible Euler equations from the hyperbolic scaling of the Boltzmann equation. This type of problem is often referred to as the problem of hydrodynamic limits.
But Benjamin, don't you want to have a short break?
Okay. At this point, I think my talk will not take more than, the remaining part of the talk will not take more than maybe 15, 20 minutes.
Yeah, okay. So, but if you wish, we can just have a short break here, and if the audience also have some questions, we can.
Okay, all right. Yes, let's just make a break here in case if there is any question before I go to the last part of the talk.
Yeah, okay. Okay, so if you have any question, if there is any question in